All right, everybody back, ready to go? We are now joined by Franklin Hu, who graduated from MIT in 1986 and has worked as a software engineer. His hobbies include being an amateur scientist looking into unexplained physics phenomena. Tonight's talk, he's going to talk about why dark matter doesn't matter. Dark matter is not needed to explain galaxy rotational curves. Standard Newtonian gravity explains the motions of galaxies when properly applied. Let's everybody give Franklin a round of applause. Take it away.
All right, well, thank you guys for showing up tonight. So I like to speak kind of an interactive talk. So are there any actual scientists out here in the audience who actually know about dark matter?
I know about dark matter, but I'm not an actual scientist.
Yeah, so just a poll. Do you guys know what dark, have you heard of dark matter? You've heard of dark matter? You kind of know something about it? Okay, well, I'm going to try and convince you that whatever dark matter is, it doesn't exist, all right? I'm not going to...
Whatever it is, it is.
I'm not going to sugarcoat it. I'm just going to try and convince you that this dark matter idea is probably one of the worst ideas in cosmology and should be abolished. So, since we're the Seattle Skeptics, why should we be skeptical about this idea about dark matter? Because it actually is one of the absolute foundations for the standard model of cosmology, which has been in business for at least 25 years. This is well accepted by the mainstream. Anyone who would say that dark matter just doesn't exist would be, well, they would just say you're crazy, you're a crackpot, you don't know what you're talking about. So people will probably think I'm a crazy crackpot, that I don't know what I'm talking about. But I'm going to try and convince you guys otherwise. So, since I'm not sure how much you guys understand about dark matter, if you don't understand something, then please interrupt. We can be interactive about this, and I can spend some more time trying to explain some of the finer points, if there isn't. So, I think the major problem, though, why we need to be skeptical about dark matter is just how many billions of dollars have been spent searching for, say, on dark matter searches. Literally, billions of dollars, right? Because the biggest embarrassment about the standard cosmological model called lambda CDM is that it's based on two things, dark energy and dark matter, and it's the biggest embarrassment that they've not been able to figure out what either of these things are, and like I said, despite the billions of dollars spent, haven't found something that they could call dark matter either, right? So, if I came up with some crazy cosmological theory that predicted everything great, but was based on the existence of the galaxy being 95% ghosts and goblins, you would probably think I'm crazy, right? Right? If I said the universe is 95% ghosts and goblins, and 5% is us, that would just sound insane. But that's actually very close to what lambda CDM is. You have dark energy and dark matter, and they might as well be ghosts and goblins. So I think we need to be skeptical about this, because if this is true, it's just like lots of money is being wasted on these dark matter searches, and we need to basically throw out the standard cosmological model, because without dark matter, it doesn't work. And if we manage to do that, then that opens up space for there to be a new theory, right? I don't know what that new theory would be, but it's got to be one where 95% of the universe is something we don't understand, right? I would think a good cosmological theory would say that, yes, the visible matter that we see can explain all of the things we need to explain without invoking all these dark things, right? Because dark just means, not that we can't see it, but they just literally don't understand what it is. They have no clue at all. So that's pretty bad. So I'm going to go a little bit over what the dark matter is. So typically they always show this one picture, which is kind of like a cartoon. Okay, so here you have a galaxy, and this top line actually measures how fast the stars are moving around that galaxy. And the strange thing is that the further you go out in the galaxy, the faster they go, right? That doesn't seem to make any sense, because it's like we know in our own solar system, the further you go out, the planets go slower. And this is exactly what the scientists calculate and predict. And so we have this lower line here, which is the expected dark matter, expected rotation from the, I got my laser pointer here, that from the lower line here, this is what we expect. We expect it to drop away as we get further. Now, because it doesn't, well, there's a couple possibilities. So one of them is that we don't understand how gravity works. Or the other one is that there is actually other mass there in order to account for this rotation curve. So, and the favored solution is that there is this mass, there is this matter that we can't see that's creating the gravity. And typically, the amount of matter that you need is like a huge amount, like 5 times as much as the visible matter in order to make this thing work. So what they do is they take this curve and they look at this curve, and then they add in enough matter so that this will work. So that is one of the main evidences for dark matter, that they're thinking, the stars should slow down, but they don't. So they just added this huge fudge factor saying, well, let's just throw it in there, okay? And that's dark matter. But I think there's some very important reasons why we should not believe that story. Okay, and my main hypothesis here is that they're simply not calculating gravity correctly. I mean, this has always been one of the possibilities, that we just don't understand how gravity works, so maybe gravity works differently, or there's something we don't know about gravity. And I'm going to assert that we've just made a foolish, bumbling assumption and have been using gravity incorrectly. The Newtonian gravity law that Newton came up with actually works perfectly fine if you apply it correctly, and that is going to be my main point here. Now, another problem I'm going to point out is that there are galaxies which actually don't show any of this anomalous rotation curve stuff. It follows 1 over r squared gravity perfectly. But that's a problem, because these galaxies absolutely have to have dark matter in them. See, these galaxies, when you do this, have calculated no dark matter in them. And that's a big problem for the hypothesis that it's due to particles. It's also a big problem for theories like the modified MOND, is another alternative theory saying that gravity actually has to change depending on whether you're in distant galaxies or whether you're in the solar system. But if you see a galaxy that doesn't have any dark matter in it, that goes against the whole concept that gravity has to be modified in these things. And so that blows away that theory. And finally, I'm going to show you some papers. You know, people don't know about these papers. They've been ignored. And I had to dig to find them. But these are examples of actually calculating gravity in the correct way, which I'll explain. And you can get the correct rotation curves. And there's absolutely no need for dark matter. And I'll also discuss some of the other reasons why people think that dark matter exists. So what's fundamentally the problem here? So what I have here is that they try and figure out what this what the expected velocity is. I mean, where do they get this curve from? That was my number one question. Where do they get this curve from? And they do it by taking the standard gravitational formula here, and they equate it against the centripetal force. And then you do some math, and then finally you get this formula, which is the square root of the gravity times the mass divided by the radius. That gives you the velocity. So if you use that formula, and you figure out how much matter is in this galaxy, and you make some simplifying assumptions like the matter drops off at an exponential rate or something like that, then you can exactly get this curve. And I've been able to exactly replicate this curve in a Python program that ChatGPT made for me. So I can tell exactly the formula that's being used to get that. But I would say that this key formula is actually wrong. That what happens is that this is not generally correct. So I'm going to try and convince you that it's not generally correct, because let's say this works like if you're trying to calculate the velocity of the moon, right? But what happens if we just took a drill and we started drilling into the Earth, so that as we get to the middle of the Earth, we try and calculate, what's going to happen here, and as we get closer to the middle, r is going to get smaller, so we strangely predict that the velocity will get faster and faster and faster, and finally, when we would get to the center of the Earth, what would it say about what the velocity would be? If r goes to 0, what does velocity go to? Infinite, which is strange. You'd think at the center of the Earth, the force of gravity would be 0, and the velocity should be 0, but instead we get infinity. So that's one reason to believe.
That's not infinity, you get undefined.
Well, yeah, you get
There's
undefined.
a big difference between infinity and
So let's say we get
undefined.
1 inch away from the center of the Earth,
Then you're
we get a
positive
really big number. But that seems wrong, okay? That's just that's not my reality. So I would assert that what we have here is really a case of mistaken identity. So, here we have the standard formula for gravity. But gravity, everyone knows this, is that it's the gravitational constant times the mass 1 times the mass 2 divided by r squared. That is the standard force of gravity that was used to calculate that velocity. However, I would assert that this is not the universal gravitational law. The universal gravity law actually says this, which is that mass of object 1 times mass of object 2 divided by the distance from the center squared. And tell me does that look like, is that the same thing? Am I making a big deal over nothing? Is it the same thing? Can anyone see what's different between those two? It's in the denominator. So one of them says distance, right? We know what distance is. It could be distance between any two things. But in this standard gravitational formula here, we have r squared. What's r? What's r? It's radius, right? And what things have radius? Well, things which are circular have radius, right? So that implies that this only works for things which are, at the very least, circular. And actually, the deal is that Newton had this problem, and the problem is that if you're standing on, say, something, and you want to calculate what the actual force of gravity is on you, so imagine this. Suppose you went to Giza, you saw the pyramids, you went to the top, and you want to find out what is the force of gravity from the pyramid on me. So then you try and apply this formula here and say, okay, I got the gravitational constant. I can say mass 1 is the mass of the pyramid, mass 2 is the mass of me, but then you'd be faced with this, well, what's the radius? Where's the radius of the pyramid? Right? You can't do it. It doesn't work. Can't apply. So what would you have to do? In order to do that, properly apply the actual universal gravitational law, you'd actually have to break the pyramid up into its separate blocks, right? So the pyramid's made out of blocks, so what you could do is that you could calculate the force of gravity between you and the block right beneath your feet. Right? There you could take the mass of one object times mass 2, divide it by the distance between the centers. And then you could do the same calculation to the next block, and the next block, and the next block, and you could do the calculation to every single block, add it all up, and then you would have the force of gravity. And that's how you are supposed to properly apply the universal gravity law in order to calculate the force of gravity on something that's like in any arbitrary shape, really. If you have a potato-shaped asteroid, you could calculate the force of gravity by breaking it up like that. But the thing is that generally speaking, it's really hard to calculate that. But Newton, back in the day, figured out that if you are in a sphere, then it simplifies things enough that you can actually do all the block counting by literally saying, I'm going to do the block in front of me, the block in front of me, the block, and then I'm going to go all the way around the Earth till I have a ring of blocks. And then, so I got the force of gravity for the one ring of blocks, and I do another block of rings beneath that, and beneath that until I make up a whole disk, right? And then I go add up all the forces. I put another disk beside a slightly smaller radius until I build up the whole right side of the Earth, and then I add up all the left. And you can see that this is a big, giant, complicated problem that actually Newton invented calculus to figure out. I mean, that must have taken him years to do this super complex calculation to figure out what is the force of gravity between the Earth and me, right? And you know what? It's not clear what answer you would come up with. But curiously enough, he came up with something called shell theorem, and it turns out that the answer is that it looks exactly like the universal formula for gravity, which is gm over r squared. It was exactly, it went through all this trouble inventing calculus just to come up with something which looks exactly the same as the universal law of gravity. Boy, that must have been frustrating. But this makes it easy for you to see that, well, this is why people make this mistake, because that formula that you get for just the sphere, right? We had to do all those complicated calculations to come up with just that. Only applies to a sphere. So, and once more, it really only applies to the sphere and where the point is actually outside of the sphere. Right? There's actually, I'll have to explain, that he actually came up with two gravity laws. They're different depending whether you are outside the sphere, which is 1 over r squared, or whether you are inside the sphere. It's actually linearly proportional if you're inside the sphere, but I'll explain that a little bit later. So what we have here is a case of mistaken identity and massive oversimplification. So I have my little cartoon here, and this has a spherical cow. And so the story goes that a farmer is having some problem with his milk production, so he's going to ask his physicist friend, what's the problem? And he goes away, and then he comes back, and he starts talking to the farmer, and he said, well, yes, I've got a solution to your problem, but, first, we have to presume that your cows are spherical shaped, or in a vacuum, and there's no gravity. And the farmer, of course, is rolling his eyes, going, what the heck are you talking about? Cows are not spherical, there's gravity, and this just doesn't apply.
They are if they're in a vacuum.
No, it still doesn't apply. So it's like, we can't say that cows are spherical, and also we can't say that all galaxies are spherical. Because basically this is the simplification that they're making. They're saying, let's just take any old galaxy, just like the one they showed you. It's flat, whatever. And we're just going to presume it's spherical. Why? Because the math is a lot easier. In fact, the only way you can do the math is if it is spherical. If it's like a disk and it's got like mass like in all different places, you're going to have to do the whole pyramid calculation thing in order to figure out what the force of gravity is, and nobody wants to do that. No one wants to do that. They'd rather just use the velocity that works in, say, the solar system, and call it good. And this is just a massive, massive mistake. That any time you see this this formula where they're calculating the velocity with square root of gm over r, they're using spherical, I'm going to call it spherical gravity law, right? Special case for spherical systems. So, what proof do we have that I'm correct about this? And by the way, this isn't even my theory. Really, nothing I'm saying is anything that I invented except for maybe the one observation I'm going to make about spherical galaxies here. But like I initially learned about this from a guy called David de Hilster, and he put this together saying that the only reason why we're getting the wrong calculations here is because we're presuming every galaxy is spherical. And that's just tragically wrong. So, he has a graphic here saying, if the galaxy is actually spherical, and he noted this, right? The thing is that this formula only works when the galaxy is spherical. Then we should find that this all works when the galaxy is what? When it's actually spherical, right? This is the only kind of regime where this formula works. And lo and behold, this is what we find, is that for these galaxies, which look like this, the very diffuse puppy ball, we find strangely that these have no dark matter, according to standard astrophysicist calculations. There's no dark matter in these galaxies, which is, it cannot be explained by dark matter theory at all. But I would predict, and David Hilster would predict, that anytime you have a spherical galaxy, you will find that it has no dark matter in it, right? So when you try and apply spherical gravity to the flat disk of a galaxy, which there are most of them, you don't get the right answers, right? So the fact that it works for spherical, this is kind of a fine point here, so I want to make sure you guys get this, right? That the formulas they've been using only work on spherical galaxies, and when they apply them to spherical galaxies, they don't find any gravity anomaly, no dark matter, right? And recently they have found like 6 of these things, so it's not just one. If you look at the papers, they can kind of explain, oh, well, the dark matter got sucked out because there's another one next to it or whatnot. So on a onesie-twosie basis, they kind of can explain it. But there's actually 6 of these things, right? And really the only thing that I can add to this whole discussion that's my own is I looked at these 6 galaxies which don't have any dark matter, and lo and behold, what do I see? I see that, there are these diffuse fuzzy balls that they look spherical. Now, I'm not 100% sure that they're, spherical, but, looking at these diagrams here and how the matter is distributed, it's like, well, that's 100% not a flat disk, right? It's probably a sphere, and so I would make the very strong prediction, if I was talking to some cosmologist, I'd say, you know what, show me a spherical galaxy that has dark matter, and I'm just going to say, no, you will never find that, right? Because dark matter doesn't exist. It's just your dummy use of application of Newtonian gravity only applies to those spherical shaped galaxies and have nothing to do with flat galaxies. So, and like I said, these galaxies present a humongous problem for the standard cosmological model because they need dark matter in order to even presume the formation of these diffuse galaxies, right? There's no way that these could have formed and not have any dark matter in them. That just, it's totally against the theory. So the existence of these just almost slam dunk rules out standard cosmological model. And another fine point is that, you know, the other explanations for dark matter, which is like the modified gravity, and in that theory it's just like gravity works well when it's at a high concentration, but the law of gravity changes when it's at a low gravity. And these diffuse galaxies, they're at a low gravity, so they should definitely be having this dark matter anomaly in it and requiring to use their modified gravity equation. So it should not ever correspond to 1/r² gravity. So that alternative is blown away. So it's like pretty much, you know, all the existing explanations, they don't work, right? So this leads to my alternative, which is that it's just due to the geometry of the galaxy, and that when we see the reason why it works sometimes doesn't work, it's just due to the correct application of gravity versus you know, using simplified, oversimplified spherical calculation to figure these things out. So you're probably wondering, okay, well, what is the correct way to apply gravity, right? And like I said, the only way you can apply it is basically by breaking it up, the problem up into like blocks, just like the pyramids, and then individually calculating every single one. Like I said, if you dig hard enough, you will find people who are saying this, is that, you know, I showed that once one considers the mass distribution of a spiral galaxy is disk-like, as opposed to being a spherical distribution, the observed rotation curve is readily recovered. So this is all you need to recognize in order to correctly recover the rotation curves. And you know, this guy, he did it, and you know, this is the same. This is the graph of the same galaxy that was on this. That's on this typical chart, and he can exactly recover the rotation curve, right, by just calculating it in the right way. I also found another paper recently, and this is my latest find, is that this is another example of, instead of doing this cartoonish, simplified calculation where you literally only consider the mass of, the total mass of the galaxy, and you make some assumptions about the exponential decay of the galaxy, and even that's questionable. What you do instead, you take a picture of the galaxy. He broke it up into 41 by 41 pixel matrix. You know, you presume how much matter is in there by the brightness. And then if you want to find out what this velocity is going to be like at this point in the middle, well, you have to calculate the force of gravity against every single other pixel in this picture. You sum it up, then you can actually calculate what the velocity should be based on the force that you come up with. And lo and behold, you know, he did a lot of different galaxies, and you can see that the little blue dots are matching exactly the actual observed galaxy rotation curves. And you'll notice that, you know, these galaxy curves are not smooth. You know, there's hills and there's valleys and there's little dips, because we see all that variation in the arms and stuff like that. None of that is captured in those super simplified calculations that these, you know, dark matter people are using, right? They don't start from a picture of the galaxy to figure out the galaxy rotation curve, but these guys do. And and so it's remarkable that they can just exactly recover the rotation curves. No dark matter is needed to explain this at all. So, you know, when I've talked to other people about this, you know, they just don't believe me. Why? Because they can't believe that for 25 years, every cosmologist has missed this, right? This is, I mean, is this like a hard problem to miss, right? It's like, I think very straightforward misapplication of how Newtonian gravity works. I mean, how could you not realize that you cannot apply spherical gravity law to a disk, right? You know, I would think that as soon as they discovered this problem and they did this initial calculation, I think their first gut should have been that, oh, well, maybe we did the gravity calculation wrong. And then they should have gone back to Newton's original equation and saw how he invented shell theorem and why the 1 over r squared gravity exists and why you can't use that. But no. But, you know, yet I talk to my science friends and they still don't believe me because, you know, 10,000 cosmologists over the past 25 years just can't be wrong, right? But imagine if they were. This would just be the most gigantic embarrassment ever, right? How could they miss something so obvious, so simple? But yet, in all my searches of the internet, I haven't seen this even brought up, really, except for, you know, the one paper by De Hilster and deep diving, digging into the internet to find those 2 papers saying that, oh yeah, you can recover the galaxy rotation curves. It's just using Newtonian gravity. So, you know, I'm still searching for, you know, the rebuttal to this argument that, yeah, you just misused Newtonian gravity. And so I'm surprised that, you know, I'm like nobody, you know, I'm just like Joe, computer science amateur, right? And this isn't even my main shtick, anyways. My main shtick is the ether and gravity and stuff like that. But I just find it, almost incomprehensible that such a simple mistake could exist for so long. Yes.
Let me know when you're ready for Q&A, because I'd
Okay.
like to queue up.
Well, you can ask me questions anytime, really.
Okay, so this is not unknown. I mean, just is the internet good or bad? Well, it turns out that I can pull it up on my phone. You know, arguments from years ago, looking at this.
Yes.
And they, of course, you know, the ones I'm tending to find are people or astronomers who tend to believe that they're right. Maybe it's how I'm phrasing my search. But so they're saying that the modified gravity approach explains a limited number of situations, but it doesn't explain the vast majority of situations that dark matter theory explains.
Right, we're talking about MOND, and I agree
Right.
that MOND does not explain away all of the
bunch of
observations
stuff, yeah.
fairly well.
Yeah.
Although I'm saying that MOND is wrong as well, because it's
Okay,
not
no argument for
actually
me on that.
it's not actually a modification of gravity. All you have to do is use gravity properly, and then you get the correct answer. So MOND is wrong.
MOND-
It's like the existence of the spherical galaxies that don't have any dark matter basically disproves MOND in a very, very harsh and bad way.
MOND is more making the supposition that gravity works different at different scales, which I don't particularly agree with.
Yeah, so how does gravity know when to switch?
Exactly. I don't see a physical mechanism where that makes sense.
I mean, it's just like a gigantic fudge factor. Say, okay, well, at this point, it changes its mind and it knows to be less, right? But you know, like I said,
We both agree MOND is not
floored
probably
that-
the correct approach.
and I spent like a lot of time just digging into the references to see, you know, is this what they're actually doing? Is this what they actually think? I mean, am I getting this wrong? Because people will tell me, say, oh, no, they're not doing that. That's what that other quote I had in there says.
MOND is also not well accepted.
But you know, so I found a bunch of evidence. You know, I looked at where where this curve comes from and what the references were and what they referred to, and you know, I have the paragraphs exactly from those papers saying that, well, here we have the velocity equals square root gm over h, and h is the distance r. So there it is. That's the formula that they're using to get this formula. It's in a legit science paper, and then they're calculating dark matter off of that. So they are definitely using this. I mean, and then, people will say these crazy things. It says like, let's simplify a bit and look at the motion of objects under the gravitational field of a spherically symmetric distribution of matter. Yes, spherical galaxies aren't spherical. I mean, spiral galaxies aren't spherical, but the results will agree to the first order. It's like, they said that with a straight face, because no, it doesn't. But they'll clearly say these things that they think they can turn every galaxy and consider it a sphere, right? So you've got all these references, and you can see this in Wikipedia, saying that they expect the velocity to decrease just like we observe with the planets, and to the question of, well, how does gravity know when to switch? Well, gravity knows when to switch depending on what the geometry is. So in the solar system, all the mass, 99% of it is located in the sun. So that is a spherical distribution. So when does gravity know when to change? If gravity knows when to change is when you're in a situation where you are actually still inside the body of mass, right? If you look at a galaxy like this one, you can see that the mass is decreasing, but clearly you are still in the middle of the mass body. It's not like all the matter is concentrated in a speck in the middle, which is what they're actually presuming. Is that actually, I told you, Newton actually has 2 laws of gravity that he came up with. And so the one that we know about, 1 over r squared, this only applies when you are in a spherical situation and you are outside where the mass is. That's 1 over r squared. But the one that the people don't hear about is the situation where you start digging inside the Earth. That if you're inside the body of mass, you're somewhere in between. And in there, you find out that the force of gravity is just proportional to the radius. And this is still a sphere, but you find out that, if you were to dig all the way down to the center of the Earth, since gravity is proportional to the radius, when you hit the center, radius equals 0, then gravity is 0. And then as you go further up, you get more dirt underneath your feet. The gravity increases. And the gravity increases right up until you get to the surface of the Earth. So gravity constantly increases when you're inside a body of matter, right? So when you look at the galaxies, there's matter all the way through, all the way to the edges. And so counterintuitively, if you were to measure the force of gravity, it actually increases the further you go out, because there's just more stuff underneath your feet. And so this kind of motivates why is it you get the curve which actually goes up, right? It goes up because there is just more matter. The further you go out, there's just more matter. More matter means more gravity, means the stars go faster. So that gives you some intuition on how that works. Now let's get to the point about what about this other evidence? Even if you could throw out the whole galaxy rotation thing, right? Let's just everyone agrees that that's not valid. There's still lots of other reasons why they think dark matter exists. So in order for me to make my point, I'm going to have to dismiss the other bodies of evidence that I just figured out. Yes? You have a question?
No, you're shaking my head.
Oh, okay. Yes.
Yeah, I don't have a science background, but I'm wondering, these formulas that involve radius in the formula, if the galaxy is not spherical, what would happen if you took the cubic feet of the galaxy and you just, in a computer model, designed it as a sphere that has that amount of cubic feet and then took the radius of that? Would that be able to tell you anything? The equivalent.
No, I don't think. I think there's like the same pyramid problem. It's like, well, you could go ahead and take the pyramid and make it into a sphere, and then you would have a radius, and then you could calculate the force of gravity. But I think you would get the wrong answer, because I think, intuitively, depending on where you were standing on the pyramid, you should get different answers. because it's asymmetrical,
I
right?
see.
So, no, I don't think that would work. There's actually really no shortcut to doing this correctly. In fact, you know, in the paper I was reading, they're saying that this is not solvable. You cannot solve this using just equations. You can only do that if it's a spherical symmetry, and you can only do that because, you know, the symmetry. But anything else like a disk, it's, you know, exponentially decaying disk, it's like you can try, but you'll genuinely get the wrong answers. The only way you can do it properly is to break it up into blocks and do all the calculations. There's just no proper shortcut that can be applied to things which are not spherically distributed to this system. So let's go over the other evidence for dark matter. So I'm going to reference this video by Angela Collier, which just says dark matter is not a theory. And there's no hate on Angela. She does an excellent job of explaining the evidences for dark matter so well that I can pick it apart and figure out what's wrong. So excellent job, Angela. So, you know, the first piece of evidence she brings up is this galaxy rotation curve, probably the most common piece of evidence. So the second piece of evidence, which is really obscure, is the CMBR, the cosmic background radiation. And, you know, she rightly points out, it's like, well, you know, that's this picture back here of the red and the white spots, and it's like, you know, it goes like, babe, it's like, this is not screaming dark matter. I mean, how could that picture say anything about anything, right? That just seems crazy. So she took 20 minutes to try and explain it, and it still didn't make any sense. So I'm going to spend considerably less than that trying to explain it. And this is all based on the standard cosmological model called lambda CDF. So, and this is where we get, I don't know if you guys seen this common pie chart where they say the visible matter is only 5%. Have you guys heard that? The visible matter is only 5%. The dark energy is like, you know, 68, 70%. And the dark matter is 5 times as much as the regular matter at around 26%. Have you guys ever heard of that? No? I mean, yeah. And when you heard that, do you not say, that sounds absolutely absurd? That 95% of the universe is this unknown stuff? Yeah. So where does that come from? Well, it comes from these bunch of calculations from the standard cosmological model. You know, it explains a lot of things. It explains how galaxies are formed, how the nucleotides are formed, what is the distribution of atoms in the universe, and it all started from a Big Bang. And one of the things it can predict is this cosmic background radiation. So based on their model, based on the universe blowing up, they can say what that picture should actually look like. And they do it based on something called, you know, a power spectrum. You've got this curve here, and what the heck that is? Well, in this picture of the cosmic background radiation, they measure the size of the dots, right? You have like a big red dot here and a big blue dot here. And they measure how big those patches are. And then the horizontal axis is how big the patch is. So to the right, we have really big patches. To the left, we have really small patches. And then the height of the curve saying, well, how many of those patches are there? So this is what they call a power spectrum. So they